If you write out the equations for the Standard Model and general relativity side by side, you encounter a dense wall of arbitrary constants. The speed of light, the gravitational constant, the cosmological constant, these are all empirically measured inputs. We know what these constants are because we measured them, but physics currently offers no underlying mathematical reason for why they exist in this precise configuration. The equations describe the universe, but they lack the capacity to explain their own origins. The Continuation Consistency Framework, or CGC, proposes a solution to this problem. Instead of starting with measured physical laws, the CGC framework derives all of physics from a single organizing principle of computational self-reference. For over a century, our physical models have relied on geometric structures. We treated space-time as a continuous, malleable fabric. Examining reality through the lens of algorithmic logic shifts the foundation entirely. We now have to ask what happens if the universe is a computable object rather than just a geometric one. In this framework, the physical laws we observe are the outputs of a computational structure that defines its own next state through internal logic. This begins at what the framework calls layer -1, with a single meta-axiom. Reality is the unique minimal fixed point of a computable self-description operator. This animated diagram illustrates configuration space. Think of it as a countable lattice of discrete sites. An operator, labeled D, actively scans and replicates this lattice. The universe computes its own next state, meaning it is exactly what it says it is. That is the strict mathematical meaning of D of S equals S. To select its next state, the universe uses minimum description length. This equation shows the formula for the optimal model. The framework balances predictive error against the algorithmic code length required to generate the model. This means the universe naturally optimizes its own continuation. It favors states that maintain perfect predictive accuracy while utilizing the shortest, most efficient underlying code. We can see specific clustered regions forming on the lattice. These are areas where predicting the state from within is mathematically cheaper than an external environment trying to reconstruct it. The framework formally defines this metric as closure advantage. When a region achieves a high closure advantage, it becomes stable. It requires less computational effort to persist than it does to dissolve. What human observers perceive as solid physical objects are actually just localized data compression hotspots surviving on this universal lattice. The question then becomes how an abstract algorithmic cost function morphs into the gravity we experience at the macro scale. This 3D topographical landscape represents the closure advantage function, undulating across a grid. Taking its second derivative with respect to displacement generates a symmetric tensor field. The framework defines this explicitly as the collective closure field. Lovelock's theorem dictates this metric must satisfy the Einstein field equations. We trace space-time's signature to computational efficiency. Time is concave because predictive accuracy degrades, while space is convex because adjacent copies are redundant, creating the -+++ signature. Gravity and spacetime do not exist as a fundamental stage where events take place. They are the mathematical consequence of information optimizing its own survival. This structural logic extends downward from the macro-scale geometry of gravity. It also dictates the internal symmetries governing fundamental particles. This diagram illustrates the deep carrier, the minimal three-dimensional complex vector space required for computation. Its internal rotations determine standard model gauge groups. Specifically, the strong nuclear force arises as the automorphism group dictating particle symmetries. Scaling down to layer 4, the framework derives the Born rule and explains how quantum entanglement emerges directly from the computational lattice. Consider two localized subsystems sharing a physical boundary, informed by a shared flow of history data. Their combined closure advantage becomes superadditive, forcing their probability distributions to merge and perfectly obey the Bell inequality violation formula. This boundary coupling mathematically forces Bell inequality violations. It proves that quantum entanglement operates without the need for hidden variables. Quantum entanglement is the strict mathematical requirement of non-local data continuation across a shared boundary. Shifting focus back out to the cosmological scale, the framework tackles one of the most notorious discrepancies in physics, the cosmological constant problem. Quantum field theory calculations for vacuum energy exceed our actual cosmological observations by 120 orders of magnitude. The CGC framework's derived formula for the cosmological constant grounds vacuum energy directly in algorithmic complexity, with spatial volume prominently in the denominator. As the universe's spatial volume expands massively, the denominator grows, naturally diluting the vacuum energy down to a tiny, non-zero positive fraction. The vacuum energy is a perfectly diluted algorithmic complexity cost spread across an expanding universe. A unified framework is validated by the rigid, testable constraints it imposes on the world. It must generate specific rules that can be checked against particle data. In Layer 7, the framework derives a specific, testable constraint concerning the Yukawa sector. This animated equation establishes that the determinant of the conic correction matrix must equal 0. This represents a hard mathematical boundary. This mathematical rule forces a specific hierarchy for fermion masses, dictating the first generation must be vastly smaller than the second and third. Comparing this constraint against particle data group measurements reveals an incredibly close fit, ranging from 0.89 to 0.99 for quarks and leptons. The framework also predicts that the three gauge couplings must unify at a precise 1:1:1 ratio at the deep carrier scale. This entire computational architecture is ultimately bound by the limits of formal logic and self-reference, much like the incompleteness theorems established by Kurt Gödel. A perfectly self-referential system cannot prove its own consistency from within, but it remains rigidly bound by its own rules. Starting from a single abstract operator computing its own state, the math cascades downward. It generates discrete grids, warps into tensors, builds fundamental particles, and scales up to form the observable cosmos. If reality is the unique minimal fixed point of a computable self-description, then the structures of gravity, quantum mechanics, and the Standard Model are the only outcomes that satisfy the requirement of internal consistency.